Okay, and I just saw that Peter Danzig joined as well. So we can thank Peter for making this possible. Peter, thank you. Just wanted to very quickly say a few words. So Peter Danzig actually was instrumental for me to get hired into NetApp. And so shortly after I got hired into NetApp, before I came to UC Santa Cruz, he actually left NetApp for Akamai. And so he knew a lot about CDNs. But then he connected me just a few weeks ago with John Dilley. And it turned out John Dilley and I actually knew each other already from back when web caching was hot, before content distribution was hot. And we actually met in Lisbon on a web caching workshop. So thank you, Peter, for reconnecting me to John Dilley again. And it's my great pleasure to introduce John Dilley, who's going to talk about introduction to modern CDN architectures. He's currently a chief architect at Raphael Systems, a startup focused on the development of edge computing technology. And before that, John Dilley spent 16 years at Akamai, where he developed the Akamai content delivery, application acceleration, and cloud security businesses. And before that, he was a distributed systems research scientist at HP Labs. He's interested in all kinds of distributed systems, from small embedded devices to internet-scale services and platforms powering global applications. So it's my great pleasure to have John Dilley here. Please go ahead.
Thank you very much, Carlos. So I intend this to be an informal, fast-paced talk to outline the structure and function of modern content delivery networks. It's really intended as a basis for discussion rather than a CDN full-blown tutorial. There will be no death by PowerPoint here. I've got some fairly basic text slides. Actually, I wasn't planning to do slides at all, but I turned my notes into something on screen because I hope that'll help with the introduction. But I'll quickly lay a foundation, and we'll explore your interests together in what time remains. And if we need more time, then let's have that as a discussion. Very quickly, the terms used in this discussion: content, by which I mean internet information, HTML pages, images, videos, downloads. Delivery is the transmission from a server to an endpoint, which can be a user, a browser, a device. CDN is a service that delivers content on behalf of the content owner. HTTP, TCP, and IP are the protocol that my work mostly focused on, and I believe is most relevant here, the lingua franca of the web. I will note that CDNs also deliver streaming content and some peer-to-peer and other protocols. But modern CDNs today are mainly HTTP, even for all that great video you see from Netflix and others is delivered over HTTP these days, and that was really nice for us at Akamai as that change happened from proprietary streaming protocols. Okay, a request for today's discussion is a single HTTP operation, mostly GET in CDNs. Some POST and some PUT happen. And I want to differentiate two terms that I don't think there's a standard definition for them. Latency. When I use latency, I mean the endpoint to server per packet round trip time across an IP network. And response time is the click to done. That's an end-to-end measure for end users for loading a web page or the part above the fold, as they say, often comprising many requests. And response time for an HTTP transaction is composed itself of the latency times the number of round trips that you have to make, plus packet queuing delay, plus your server residence time or think time. Quickly, some CDN benefits. They help simplify resource provisioning for a content owner. This is a business benefit that they provide. They accelerate delivery through low RTT and a scalable delivery architecture. This low RTT speeds up TCP three-way handshake and the three-way handshake of setting up a secure session if using HTTPS or the Transport Layer Security Protocol. This alone is enough for some large consumer electronic and auction brands and others to build their own edges, even if they have otherwise uncacheable content. That speed affects the user perception, and there's a translation of user perception of performance into dollars that's been well established. CDNs also provide improve availability by having resources in many locations to help absorb traffic spikes and to mask wide area network availability issues to some degree from time to time. It's not obviously perfect. If you need to talk to an origin server, then you need that WAN. The multi-tenant architecture of a CDN also helps to spread cost across many participants. So for a single organization to develop that level of availability, they would have to have a minimum number of servers in each and every location. And then as an individual organization, that tends to be expensive. And also within a CDN, not every customer spikes traffic at the same time. So there's a little bit of economy of scale there. CDNs typically function, maybe always function, by directing endpoint requests to nearby available resources. And we'll talk more in detail about this. And they provide greater elasticity of server resources than a typical single origin server can provide. Again, that's in part because of the multi-tenant nature. The operational model of modern content delivery networks, and historically even, the machines are operated by a provider, outsourcing the capital expense and operations. The CDN owner will establish many relationships with data center providers for a non-provider CDN, I should clarify. So the non-provider CDNs, like Akamai, Cloudflare, et cetera, they contract for space and power. Carrier-provided CDNs have their own space and power. So this obtains access to many locations. And again, it's harder for any individual company to do this. The CDN owner then handles the network and system management and 24/7 operations, deploying and monitoring servers, keeping ahead of the aggregate scaling demands across the entire customer base, which is easier with many customers on the platform with the way spikes appear. There's going to be a spike soon with the US March Madness. There's a spike with hockey and other sports as well. So they are spread in time. And the CDN operator keeps servers updated with security patches, which is super important, and keeps them operating efficiently. And running as a service, you can more quickly iterate and roll out performance improvements. We'll talk a little bit about some of the CPU enhancements that you can make. And so as a service provider, you can roll these out more quickly than an appliance type approach would allow. Deployment modes. So the Akamai model and others deploy in many locations to get servers as close to many or most users. And these tend to be smaller locations, so more smaller locations. Optimal cluster size, I'm saying 4 to 20 machines in a given location. Of course, this number depends significantly upon traffic, the end user population in a given geography or network, and the content access models. And your mileage may vary, and I'm leaving time at the end for a few of my observations and for discussion on this with the IRIS-HEP team. Machines are typically disk heavy, 6 to 8 rotating media or SSD volumes are not unusual. CPU in a well-tuned CDN server is, I call it like a bit shovel for cacheable workloads, pulling data off disk. Now, in certain platforms these days, you can also use zero copy techniques like the send file system call to avoid the bit shovel issue, and with a little bit of additional changes in terms of the management of connections in the core proxy. But nice thing about send file and this type is you don't pull all of the data up into application space before sending it back down to the network card. It goes directly from file system buffer cache into the NIC. And this may be a good technique for what you guys are looking for, especially given the, well, okay, let me not go there too much right now. Other delivery models besides the above use fewer and larger locations. So you'll see this housed by some of the cloud providers or other large organizations. They'll put a few locations with many servers in each. Adding a few more network hops eases the operational burden because you don't have as many contracts to form with ISPs, and you don't have as much scaling challenge of a lot of small points. You can scale one large location a little easier. So something to consider, which model makes sense for your community. If you are contracting with one or perhaps have the resource to build one. There's a trade-off of latency against operational complexity in this model, as I'll note. Okay, cacheable content delivery. So the CDN can quickly deliver repeated content requests from cache. That's the beauty of it. The second to nth requests can be served without WAN interaction. Whether the WAN is even up or down can be masked, as I noted earlier. Web content typically has very high recurrence. You see 90% plus cache hit ratios commonly for web content. Right, the popular requests get many hits. Your common JavaScript and CSS and base pages and so forth. You see this both in the time domain and the temporal domain and spatial domain. The requests per object are high. So I used to look at this a lot back in the day. And we'll see high memory hit rates as well for modest-sized objects, which is a nice optimization that you can make with high memory space. Whether that applies to large objects is a discussion topic. There are other ways to tune for very large objects, leveraging file system buffer cache. I have seen that be a better approach for downloads than storing in application memory. Let the file system do it. We generally use a demand-driven cache model for efficiency. Content push to pre-populate caches is a recurring thing that comes up with with customers and content owners. They think that's a great thing, but I will note I've never liked this model. So this is my pet peeve, I suppose. It only helps the first requester. The second through the nth during a time to live interval all get the same performance, which is the fast performance from cache, and you've definitely spent bandwidth and displaced things in cache to make room for the pre-populated. So think about that carefully. But in your domain, this may still be meaningful. Even though it's not my favorite thing, there are domains in which it is meaningful, perhaps for the first scientist working on, one scientist working on a data set for that day. So we use time-to-live based cache coherence to trigger refresh checks after the TTL expires, and we have some nice ways to optimize that by pre-refreshing it getting near the end of the TTL. But I understand with your IRIS data sets, actually, they do not change. So immutable data is absolutely the best for a cache workload, which is pretty obvious. Some challenges: uncacheable content and whole site delivery requires some different techniques, which I'll talk about. Operation at scale is one of the key challenges, and mapping and traffic steering, identifying where to direct traffic. So as I talk about content delivery, these are some of the big challenges that anyone building a CDN needs to think about and build for. And finally, tuning for high performance. It's a relatively narrow population who have this fairly rarefied skill set here to tune very high performance infrastructure at scale, but it saves you potentially a lot of money. 1% of CPU shaving in a 100,000 machine CDN is 1,000 machines you don't need to buy as traffic ramps in the coming interval, right? So this is assuming a growing business model, which every CDN I'm aware of grows over time. Actually, that's not true. Let me walk that back a little bit. Not every I'm aware of. But tuning for high performance is important. So if we were all in a room and I had a whiteboard, I would start with this graph, this picture, by drawing it, starting with the smiling face at the bottom, and we might not have any other words or anything. But let me walk quickly through this. A DNS-based CDN tends to operate as follows. The end user makes a request for a host name. That host name, that request goes to their DNS resolver, which asks the CDN's top-level name server for the IP address. It found the top-level name server by going to the root name server and the .com or .net name server and so on. So the DNS resolution proceeds in that way until you get to the CDN. And in this conceptual model, the top-level DNS server returns a name server record for a name server in the nearest location. So the first step resolves you to your best edge location. That's presumably the one that's nearby and has sufficient capacity, aggregate CPU capacity and bandwidth. Resource capacity in general, because disk capacity is an important factor as well. But it will resolve you to an edge location that has available capacity. The DNS resolver then repeats the DNS request in step 3 to a low-level name server in that edge location. This is coming directly out of the Akamai top-level, low-level model. And others behave similarly, and others behave differently as well, which I'm going to get to at the end. So the resolver then asks the low level for an IP address and gets one or more IPs for the requested hostname. It's always nice to have more than one, because user agents, browsers, and so forth, if they get a failure to connect to an IP address, will try the next IP address handed out. And then you can use that to hand out 3, 4, 5 to spread load heuristically across the web proxies in that location. So in step 3, the return answer from the edge location to the DNS resolver is returned to the end user. Now they have IP addresses. They open a TCP connection, do a TLS handshake potentially, and send a browser request to the IP address of that proxy, which will send a request forward to an origin server. The origin server in this case is the customer's location where they have application servers and database and what have you. And this is the location that's authoritative for the content. The cache is a surrogate for the origin server and not authoritative for the content. So that's why it must check every now and again at TTL intervals and so forth. And of course, if it's uncacheable, you'll always take line 5 up to the uncacheable resource at the origin. The proxy caches the response if permitted and sends that response to the end user completing the transaction. This is actually a good time to pause. I'm about 20 minutes in. I want to talk no more than 20 more minutes, and I think I'll be a little less than that and leave a lot of room for discussion. But I would like to pause here for some of that discussion in case there are any questions about the model. It's not my best picture, but hopefully it's okay. If no questions, Yeah, go ahead.
Sorry, go ahead.
One thing that's maybe interesting is we're working with a lot of independent sites, different data centers that are contributing resources around the world. So it's been historically kind of problematic to integrate with DNS. And certainly at the commercial level, for commercial CDN, it makes no sense to behave independently of DNS. But have you ever seen anybody who tried to do some of this at the application level to discover, basically you're doing edge discovery there?
Yes, so there's a couple of things in there that let me try to tease out. The last one first, application level, there is a protocol for content naming and location, whose exact name I forget, but I can pull up here in a bit. But the idea is names are unique and persistent, and the location of content can vary over time. That kind of model may make sense in your environment, where I believe you have you said you have many data center resources distributed across multiple organizations. Such a structure could be possible. Integrating many content providers into a single CDN sounds like it may be the challenge you're facing.
I think, John,
are you thinking of NDN?
NDN, thank you. Yes.
Yeah, exactly.
Data networking. Mm-hmm. There was another comment.
Yeah. Just a quick question. Is there another line here that goes between the edge location and the top-level DNS, or the edge location that basically informs the top-level DNS of its availability?
Yes, absolutely. So the monitoring system is not represented here at all, nor is logging. All of that comes in the next set of lines. Yes, you're absolutely right. And one reason for this top-level, low-level structure is because keeping track of individual machine details is a larger problem set. And that's why the Akamai solution started this way. This is a historical picture from Akamai, actually, and it's illustrative in that regard. But it's better if you can make just one request from the DNS resolver, and I believe that is how the current system works. One other comment here is, instead of this approach, this may apply to Brian's example. You can also make a request to a name server and get back an Anycast IP address. We used in my work then and my work now Unicast, where an IP address is terminated at one location. An Anycast IP is presented by many points of presence on the network, and then BGP, the Border Gateway Protocol, and IP routing direct you to the IP, the location where that IP is advertised with the fewest network hops. So that's another model that some CDNs are using, and many are using especially for finding a DNS server. So they have different benefits there.
So, John, really quick question is, so I remember that there was this term of Akamizing a web page. Can you say a few words on how that fits into this picture? Or are you going to talk about this later?
No, I wasn't going to talk about Akamization. I don't have any slides on that. So briefly, what that is, in the days before Akamai could deliver whole site content and uncacheable content, a web page, an HTML page, had to be modified such that image references for cacheable content that should come off the CDN were rewritten, putting metadata into the URL to identify certain properties of the content, including a billing code, if you can believe that showing up in a URL, but it did, and some of the load balancing and TTL and coherence information. That was all put into the URI that was served by the page. So customers had to edit their HTML to do that. This was, of course, heavyweight and limiting to the the product. So whole site delivery was added, and that was one of the challenges in the previous slide. So if I was to try to solve the challenge Brian mentioned, I would start with the toolbox that I have here, and I would provide DNS names related to the resources, the content structure, if you will, at each of the content owners, and provide a mechanism for updating that in the DNS on behalf of the content owners. So I think there's potential for that. Maybe there's a whiteboard discussion that we can have to follow. Any other question on the model? Otherwise, I'll move on. And we can always come back to this later. So in the cache model, there's some optimizations that we can provide. For example, consistent hashing for placement of objects within clusters. This serves to put objects on the minimum number of servers, typically at least 2 in each location. The objects are located actually, or placed actually, by demand. So only when first requested will an object land on one server, and if a request goes to a second, then it will be loaded there by in-cluster cache sharing. When there are changes in cluster membership, there's no object movement required immediately. So future requests instead gradually redistribute content to new or different servers. New servers get content when a server is added to a cluster. If it is the head of the consistent stride for that piece of content, one way or another, then requests begin to arrive at that server, and it demand loads the interesting content at that point. And typically, it will load it from peers within the location. One more thing I didn't show in this previous chart is edge locations can make requests to peer locations in the CDN itself rather than going direct to the origin server. So that's a parent-child type of hierarchy. So I mentioned if new servers are added to the clusters, if a server goes down or is removed, requests likewise will go to additional servers in the area, and they're demand loaded in the same way. And then more servers can be brought into a cluster to handle load spikes, and more servers. I'm sorry. What I mean here is more servers that already exist in a cluster can be brought into service for a given piece of content to handle load spikes for that content. One of my favorite examples was midnight UTC, Friday night, Saturday morning. There was a trigger for an antivirus download from around the world. The clocks were synchronized on end user devices within seconds to minutes. You could actually do a pretty good study on that. And the load spike was severe. As a result, you need more than a static allocation of servers in a location to begin serving. So as you're looking at CDN architectures, the ability to spread load dynamically is very, very handy. There's another interesting optimization to store very large footprint content. and store it only once per cluster. This applies to a content owner who may have millions or tens of millions of small objects. For example, small images, small pictures of profiles or auction objects or whatnot. Total footprint, the total object footprint is too great for any single server. So if you have a dozen servers, by storing each object once, you maximize the total footprint. You utilize the total disk footprint of the whole edge location. This applies also to large objects that are stored contiguously. You can store large objects as chunks as well. But large objects stored contiguously, if you have content spreading, the available disk is reduced because you have the same popular objects stored in multiple locations. So the techniques to do this can route a content request to the primary for that piece of content within a cluster. This trades off cluster footprint for availability and performance. So if the primary goes down, all the requested content must be loaded onto the secondary for that piece of content. And there's an additional network hop. And this roughly doubles the CPU for cacheable content if you are in the bit shovel model, and still uses kernel CPU in the zero copy case. Okay, that's cache optimization in a cluster. There's also the possibility of WAN optimization. So a large footprint, now I shouldn't have used the term footprint, but a large server base in many locations allows a type of optimization of wide area network request using the existing cache servers as an overlay network. In this way, a request can go from peer to peer within the network and potentially achieve a set of benefits at HTTP, TCP, and IP layers. At the HTTP layer, using persistent connections of the HTTP 1.0.1.1 and later is very valuable, especially with CDN peer or parent servers. What we find is that there's a lot of recurrence between peers in a hierarchy, and those persistent connections are super valuable because you don't pay the TCP or TLS handshake startup costs. You have to be able to hold many connections in at the same time. In the early days, this was not the case. The CPU cost was a function n squared of the number of open connections, and some good work turned that into order 1 rather than order n. Of course, the memory is still order n, but modern CDN servers can typically sustain tens of thousands, if not 100,000 current open TCP connections. So when they are valuable to improve end user performance, they can be held for quite some time. So persistent connections are great. At the HTTP layer, there's the opportunity to do what's called transfer encoding. If you already have an encoded data set, this won't help you. But if an origin server is returning HTML, for example, maybe a 60 kilobyte HTML page that's dynamically generated, at the first hop nearby the origin server, a surrogate, CDN surrogate, can compress that and send 1 packet for every 10 that the origin sent across a wide area network. That helps considerably because you can't do better than the speed of light in fiber, and so you have a fixed bandwidth delay product that that limits the amount of actual bandwidth you can sustain. So this parsimonious use of that bandwidth helps considerably. At the TCP layer, CDNs will optimize transport settings from the endpoint forward to the origin. Also, really the endpoint to the client, although there's only so much you can do with from the CDN. I say CDN endpoint, and that should be really CDN server. Talking to endpoints, you can't change their TCP stack, but in the CDN network itself, you can and do see TCP stacks optimized for congestion control. Some of the techniques, and these are going to apply to IRIS-HEP, are using large TCP window sizes. That gets you more effective bandwidth over a wide area for a given latency. So if the latency is over a certain amount, a larger window size helps tremendously. Congestion control algorithms. There's evolution in the TCP congestion control algorithms, and so using modern and appropriate congestion control for large object, large streams can materially improve performance. And fast opening TCP windows can help as well. One thing that I was always a little nervous about was in a large delivery network, if suddenly you do something congestion control wise that is not globally appropriate, if you're swinging double-digit % of global traffic, then it can cause congestion issues in the interior of the network, overloading routers and so forth. Modern congestion control algorithms sense queuing delay, not packet drops, but queuing delay in network equipment, and that tends to be much more effective in controlling congestion while maintaining performance. So whether you have the opportunity to do that given the network infrastructure that you have access to, I don't know, but that's something to think about. And finally, at the IP layer, identifying congested routes or congested routes appear to have high delay jitter, which is a killer for especially live media like video and audio. Or with BGP damage, if you can identify them and route around those, then that's a significant IP optimization. Funny story, in my current company, I observed a BGP route from an edge location we're running in Singapore to a cloud provider's data center in Singapore, was routed through Seattle. So packets between those two had hundreds of milliseconds of network latency, and the response time was similarly impacted. Going from that edge endpoint to a different cloud provider in Singapore went directly to Singapore. This is what I call BGP damage. The Border Gateway Protocol is how ISPs peer with each other. And as Avi Friedman, one of our early friends at Akamai, said, BGP is not a protocol to optimize end-user performance. It is a tool with which ISPs do battle with one another. And that's because with BGP controls the flow of traffic, which controls the flow of money. So one example of how you can do this, identify impacted routes and do something about it, is to measure actual latencies. And if you see a Singapore-Seattle-Singapore hop, instead of going the native, let IP routing do its thing, make a hop from your CDN edge endpoint to another CDN edge server, if you have this capability, or even some other server, and then go that way. If you draw it, as A, B, and a middle point C, the triangle inequality does not hold. A, C, B is a shorter latency than A, B in this case. So those are some of the optimizations that we can provide. I want to say just a few words about CDN security. If you have a copy of the slides, I've changed this a little bit since the upload. I just want to point out, and for this audience, it may not be totally appropriate, but quickly, security services are a natural fit with a content delivery type of network, particularly DDoS protection. You can prevent inbound attacks, deflecting all kinds of garbage traffic. The CDN can drop most volumetric traffic at the NIC. It doesn't have to go into the at the NIC or at the kernel level. It does not have to go to the application level. So reflection attacks, which you see using UDP with DNS or NTP, SSDP, these kind of attacks let an adversary wield more bandwidth than they actually have by reflecting off of victim endpoints, which can magnify their attack traffic by 10x in some cases. SYN flood attacks and other garbage TCP don't amplify, but they cause resource exhaustion at endpoints. And the CDN, as a wall in front, can deflect these at very high line rates. The proxy, typically only listens on ports 80 and 443 on TCP, so the kernel will drop that garbage at line rate. And note that the ingress, the in-link of the box, is typically not the bottleneck in a CDN use case. The bottleneck resource is either the egress link to the endpoint or CPU, or depending on the workload, perhaps disk. So dropping inbound traffic is almost free for CDN servers. And then if the requests are clean, in other words, they're valid HTTP requests for a customer of that CDN, then the most expedient thing to do is to accept the request and deliver the content as quickly as possible. The goal here being the CDN has greater capacity than the adversary, and in a well-portioned CDN that should be the case. So you just deliver the requested content as fast as possible, get it over with, and record the attack. Then later, you can apply forensics to the log stream and identify attack endpoints and do other more intelligent things. On the topic of more intelligent things, you can scan for content attacks against databases or end-user credentials or whatnot. And given the scale that the CDN wields, you can do this at great scale. Of course, with content type attacks, it's also important to do apply the same domain at the origin server for defense in depth or layered security. There's no one technique or one server, in my opinion, that can for sure do everything. So high security environments justify having both your CDN for protection out in the cloud, as well as application delivery controllers or whatnot in the origin, and then database protections layered on top of that. That concludes the prepared remarks. So I'm happy to take any further discussion on what's here and what's next.
Let's thank the speaker. So, any questions?
Yeah, I was wondering if you could say a little bit about data integrity in terms of how do you're right. I mean, academia tends to be so poor that doing things like preventing inbound attacks is not necessarily high on our list, but data integrity and delivering the right bytes to the scientific application really, really is. How do you tend to see CDNs detecting corrupt data that might be cached and ensuring the right data travels to the consumer?
Yes, Brian, great question. Funny anecdote for in case of a CDN that may be carrying, actually that anecdote isn't appropriate. Sorry, we'll have to discuss that one over a beer. Data integrity is very important in the business domain as well as the scientific domain. Some techniques for improving integrity. One that we applied back at Akamai was to add a CRC check to each disk block, and in the process of fetching content back from disk to check that CRC. We used this for a little while, but actually quit for a couple of reasons. One, it was very expensive. Two, it was impactful to the user experience in that if you detect a CRC error partway through an object, you have no choice in the HTTP but to close an incomplete, and then an incomplete download with HTTP 1.0 without content length header is actually indetectable. And also the CRC didn't always work if the data was corrupted when it came in. But nevertheless, providing data integrity at the physical layer is the place to start. One thing that you can do after that is to break content into chunks, compute an end-to-end SHA-1 or media integrity measure, and compute that block by block as well. Then, as large content is downloaded, you detect that that each block is valid, and then you have a mechanism to do an end-to-end integrity check. This technique is available I think it was first available in BitTorrent, and was leveraged in the Akamai peer-to-peer download client as well. And I don't know the status of that, if it's if it's freely available or whatnot. But that technique is a handy one to ensure that the content that you have fetched is exactly what was intended. There are other techniques, one of which is, especially as you have immutable content, when you compute the content, you can provide content metadata that includes its SHA-1, SHA-256, whatever your favorite is, hash alongside the object, or potentially in the URI itself. So as you fetch the object, if the content, the integrity check, SHA-1, does not agree with the integrity header in the URI or in a body field like an E tag, then you can use that to detect that there's been some kind of content corruption, and then you have to identify where it came from. Now, if you use TLS, content integrity is provided for you in the transport. It doesn't provide content integrity coming from disk to, when it goes from clear text off of disk to into the TLS. So an end-to-end integrity check is still useful, but we found that use of TLS in the web dramatically improved the reliability of downloads. So that's a step forward, and then using embedding a MAC in metadata in response header or URI is another good technique.
So I guess I had another follow-up question, unless somebody else wants to jump in. All right, hearing nothing else, but so one of the unique things about, or somewhat different aspect of what we're doing is the fact that we're working with processing very large data sets. And, I mean, some cases the working set size may be as small as a couple hundred terabytes, but in a lot of cases when we're really going through petabytes of data, we're doing a stream processing. We read it once and almost guaranteed to never read it again. What sort of techniques or design considerations do you see people, or I guess is there similar cases in the industry, and what techniques do they use to handle things like that?
Yeah, great. So you have a large working set. Terabyte or petabyte data. If it's not local to the investigator or the user, whoever it is, one technique that can achieve good performance is what I call move work to the data. So this is a common technique in databases and so on. If you can ship the query or the stream processing to where the data lives, then you avoid the transmission. You need CPU and CPU resource and access to the data and the I/O subsystems. But if you're able to access it over the network, you have the latter, and the former is a matter of perhaps agreements between organizations to provide compute. Alternatively, you can provide that compute external to the organization through a service provider or some federated environment that maintains high bandwidth access to the data where it lives, and scalable compute, where as a content owner you could push a container that has the stream processing logic into that location nearby that data set and run compute there. In fact, we're seeing that as a driver for edge computing in my current world. So moving work to the data, I think makes a lot of sense for these data sets, especially in a high latency and multi. If you don't control the intervening network, if it's open internet, then you can never be sure what you're going to get.
I have a follow-up question on that, actually, if you let me.
Of course.
Okay, sure. So let's say that you want to have this kind of model where you're sending work to the data, but you also, let's see, how can I say this without drawing a diagram? So you want...
You have a whiteboard, you know.
Is there really? I've never tried it. Well, no, it would be more useful for me to try to think of how to say this well rather than try to figure out some new tool in video. So you talked a lot about caching, and you want to make sure that you have one copy of the, actually you said 2 copies of the cache. What if you wanted to combine a caching model with sending work to the data model. So somehow the, if you take your job and you split it up into 100 pieces, you've got 100 partitions of the data. How do you get the work to the data if what I mean by the data is some local cache of the data rather than the original copy? Because if it were the original copy, then you would be load distributing your work in a way that exactly matches the distribution of storage, which is coupling two things that could be very different. You could have very popular and data sets and very unpopular data sets, and you wouldn't want to, like Hadoop, send the work to exactly where the data is permanently stored and just get a highly peaked usage of your CPUs.
That's a great point. There might be a piece of data that's permanently popular or transiently popular, and when it is, there's just not enough CPU at that time. So
yeah.
So in that kind of model, it probably makes more sense to, it absolutely makes more sense to use a caching model. So if there are multiple locations interested in accessing a particular data set, then the first access pays the cost, the time, the total response time to fetch that data set into a location. After that, everybody in that location or with access to that location has high bandwidth access. So that's where the CDN or distributed storage plus edge compute model will make sense. So the move work to the data model, that works at, so yeah, if we had a whiteboard, it would be great. Envision, if you will, a graph showing number of accesses and total size, and there's that trade-off. So as you get number of accesses above the line, you're better off making that wide area request, pulling the data, and then processing it nearby. Now, if you use a CDN model, the CDN does not have arbitrary compute capability, but if the edge location, if you use a commercial CDN provider, they have their own edge locations. If you have a CDN-like solution that you build yourself, then you have these edge locations, and if they have very high network quality, high bandwidth, low delay, low jitter, if they have high quality access to the data sets, then everybody's compute that is in that location will benefit. So,
yeah. Okay. So if we wanted to set something like this up, the scheduler for the work has to know about where the cache is located. Do you have any suggestions for what tools can actually do that?
Where cache is located. So starting at the most simple, you locate your nearest cache and demand load it. On the spectrum is the named data networking, NDN, that we talked about, which is a way of providing data resource location in metadata, and so a scheduler could leverage that. And another option is the do-it-yourself, if you will. But I guess one of the follow-up investigation items is for the data set, for the size of the data, how likely is it that a demand-driven cache model with appropriately sized edge locations can deliver what you want? And appropriately sized edge locations is using the terabyte, petabyte working set, acknowledging that there may be multiple working sets active. I would certainly recommend sharding the content objects into multiple megabyte or a few megabyte chunks, caching each of them separately. If you have a data set that has spatial locality properties where only part of the data set is interesting, then they'll just request the same chunk. One thing you may find is that the first few chunks are often more popular, and the end of the data set someone may drop off. So a cache only has to store what someone actually finished the download for. So.
Right. Okay, thanks.
Certainly.
Do we have time for one more?
So, I just had a very quick question. So you actually started to touch on some of this in the last answer, sharding the files into smaller bits. Many of our files are quite large, and much of the data in a single file is quite cold, and then some parts of it are hot. So this sharding idea is, I think is quite relevant. But it also leads to the question of, if we really sharded all of our files, the number of objects would be, well, I would think they would be insane. What are the order of magnitudes of numbers of objects these caches the CDNs are comfortable handling?
Millions per location. Millions, okay. I would say. So if you have so that's something you may want to consider as you choose the shard size. And millions, that bears further investigation. So I would not say that's the final word in it, but that's a parameter that we need to look at. Large, mostly cold data sets. This may not be viable, but if you can break a large, a large gzipped file, for example, into, if you expand it into a directory with individual files, you may find that 100 of the files never get referenced and 5 of them do. And if you zip each of those independently or compress however you compress, that may be better than having a gigantic archive that someone has to download and then parse through.
Yeah, our data actually, the way we currently store it lends itself to doing something like that. So that making a single file actually small pieces would require modifications at both the server end and at the client end, but it's not unheard of to do something like that. So millions. All right. So each of these endpoints is we're talking terabytes worth of storage space.
Each edge location, many terabytes. So an individual server easily holds terabytes, and the number of objects that an individual server holds, that's in the millions. So across a cluster, you're going to multiply by the number of servers, So look at a streaming video, right? You have a many gigabyte object that is the entire video, and actually it's dozens of megabytes for the mezzanine image, the original content that's translated into MPEG dash or whatever, and the CDNs will cache those in few second chunks and serve those out. So you have thousands upon thousands of chunks per video object and many video objects per edge location. Unfortunately, I don't have hard numbers, so I'm hand waving, and I should stop hand waving. But
no, but that's okay, because this is the right order of magnitude. I think this video example, short of our data sizes, the way we would split a file up, I think, is probably close to what you're talking about for video.
Yeah. Good.
Hi. Can you hear me?
Yes.
Hi. So I actually just a question. Are there examples of CDNs where you return data from edge nodes? So, I mean, one of our key issues is that we process some data, we return data objects of comparable size to what we just took in. And these have to then propagate out. And are there any setups where you routinely do things like that?
I misunderstood your question. So origin server returns a large download to a CDN edge server. The CDN edge server serves that entire object to the first visitor who asked for that antivirus object or whatever.
Right. But in our case, say, we would have a situation where the client, the final client, would then produce some other data that was to be shared with, reintegrated into the set of objects available to everyone else.
Now I understand. So the endpoint is also a content provider in that case. The
right, yeah.
Derivative object, or the computed upon result, would be stored persistently, integrity checked, and then provided with via a URI that referred to the location where that client had stored it. This is how I would think of how to structure that. The client the entity that downloaded the large object and worked on it for a while would have access to storage, and that storage would have to be able to have a name, right? So it would be Peter's server / metadata / file name that you would then share with whoever wished to consume that content. They would then pull a request from that location. If that Peter's server was a CDN-based hostname, then the DNS resolution, as we saw in the slide here, would go to a resolver and find the nearest edge location. For you, it would be the one that just pulled the original content from far away, probably. For someone else across the world, it would be their local location. And if this content has sufficiently high recurrence, then the value of the cache pulling that content across the wide area network for that population across the world would then be would then pay off. So yes.
Okay, so this winds up being a little more peer-to-peer and a little less top-down.
Well, yes. Yes, it is a peer-to-peer style of model, and the description that I used encapsulated it as a content provider and cache model. Either approach works. The peer-to-peer model has some nice advantages to it. Yeah. I don't think we have time to do a compare, and I haven't prepared for that material, but if we'd like, I'm open to spending a little more time with you guys. Great questions. I always enjoy an audience that asks good questions. I just wish that we were all in front of a whiteboard together. That's always the best. Any final questions? All right. I will thank you all for the time and the questions. It's been my pleasure to be here with you.
Thank you, John.
Definitely. We very much appreciate your time.
Thank you.
Thank you so much.
You bet.
Bye.
Bye.